Welcome, dear students, especially the students of PG Chemistry will benefit with this video. This is a topic from Statistical Thermodynamics, and if you remember the presentation which we have seen earlier to this, in that presentation we have discussed about what is partition function, the introduction to partition function, and we also discuss, if you remember, the significance or applications of partition function. Today in this video, myself, Dr. S.M. Thorat of Sri Shivaji College of Arts, Commerce and Science, Akola, is here with a very important topic, that is types of partition function. Molecular partition function for an ideal gas. Molecules are associated with energy of different types. All these forms of energy must be taken into account while mentioning the partition function. The molecular energy levels needed for the evaluation of the molecular partition functions are obtained from the solution of the Schrödinger equation. According to Born-Oppenheimer approximation, the total energy of a molecule is composed of contributions from the translational, rotational, vibrational, and electronic modes of motion. So we can write the total energy here is the addition of translational modes of motion, then rotational, then vibrational, and electronic modes of motion. So the equation holds good if there is no coupling between the different modes of motion. The electronic energy epsilon electron can be obtained for the simple atoms. The molecular partition function we are representing by Q is given by Q is equal to summation Gi into e raised to the power minus beta epsilon I. This is equation number 1. The total partition function of a molecule is the product of the translational, rotational, vibrational, and electronic contribution. So here we can write the total partition function Q is said to be the product of the individual translational partition function into rotational partition function into vibrational partition function into electronic partition function. Now first we will begin with the translational partition function. For a particle of mass m which is moving in an infinite three-dimensional box of sides A, B and C, assuming that the potential is 0 within the box, the energy levels are obtained by the solution of the Schrödinger's wave equation and are they given by the expression epsilon nx into ny into nz, that is equal to epsilon translational, that is equal to h square divided by 8m for three-dimensional box, n square x divided by a square plus n square y divided by b square plus n square z divided by c square, where each of the quantum numbers nx, ny and nz, they change from 1 to infinity. Now using the equations 1 and 3, the translational partition function, if we neglect the degeneracy, is given by Q translational, that is equal to summation nx into summation ny into summation of nz exponential minus h square divided by 8m kt, in bracket we write n square x divided by a square plus n square y divided by b square plus n square z divided by c square, where this triple summation, it is taken over all the integral values of nx, ny and nz from 1 to infinity. The motion of the particles in the three x, y and z directions being independent, we can replace the triple summation as a product of the three summations. So here we can replace this summation as a product. Here we are writing the product of the three summation. So Q translational partition function, that is equal to summation nx is equal to 1 to infinity exponential minus n square x into h square divided by 8m kt a square into summation ny is equal to 1 to infinity exponential minus n square y h square divided by 8m kt b square multiplied by summation nz is equal to 1 to infinity exponential minus n square z into h square divided by 8m kt c square. This is equation 5. The spacing between the energy levels of a particle in a three-dimensional box is very small as compared with the thermal energy kt. So hence we can replace the summation here by integration. So accordingly, equation 5 becomes Q translational is equal to, here now we are replacing the summation by integration, integral 0 to infinity exponential, that means e raised to the power minus n square x into h square divided by 8m kt a square into dnx multiplied by integral 0 to infinity exponential minus n square y into h square divided by 8m kt b square into dny multiplied by integral 0 to infinity exponential minus n square z into h square divided by 8m kt into c square into dnz. So that is equation number 6. Now if we take the knowledge of this particular formula, that is from calculus, the standard integral formula 0 to infinity e raised to the power minus a into x square into dx. If you are having such a type of standard integral formula, then the answer is 1 upon 2 pi divided by a square raised to the power half. So applying this standard integral formula to evaluate this individual integral, we write the three integrals in equation 6 which are identical except for the constants a, b and c. It can be calculated giving q translational, that is equal to a divided by h 2 pi mkt raised to the power half into b divided by h 2 pi mkt raised to the power half into c divided by h 2 pi mkt raised to the power half. So how we have got this step? We have applied this standard integral formula to each of this integral, and according to the standard integral formula you have evaluated the answer of these three integral and the answer is given in this step. Now this step, suppose if we combine, you can see that h into 2 pi mkt raised to the power half, this is common in all the three. So 2 pi mkt divided by h square raised to the power 3 upon 2 multiplied by a into b into c, that comes out to be 2 pi mkt divided by h square into v, that is where v is the volume of the box, that is abc. This is equation number 8. Equation 8 denotes the translational partition function depends upon the volume and the temperature. V is the volume of the box in which the molecule moves. Now equation 8 can be written as Q translational, that is equal to Q0 translational into volume V, where Q0 translational, that is the partition function per unit volume. If m is the mass per mole, then m can be written as small m can be written as capital M divided by Na, that is Na is the Avogadro's number. And if you substitute the value of Boltzmann constant K as universal gas constant R divided by Avogadro's number, the equation becomes Q translational, that is equal to 2 pi mRT raised to the power 3 upon 2 divided by H cube multiplied by Vm divided by Na cube. This is equation 10. And in the case of a perfect monoatomic gas, the molar partition function is given by Z is equal to, here we are representing the partition function by Z, that is equal to 2 pi mkt raised to the power 3 upon 2 divided by n into h cube into Ve whole bracket raised to the power n. Thus, translational partition function Q translational is the sum of all possible translational energy states which could be represented using 1, 2 or 3 dimensional models for a particle in the box equation depending on the system of the coordinates. Now next we are going to discuss about the partition function for diatomic molecules. That is, here we are going to discuss the rotational partition function. Now the partition function for rotational energy of a diatomic molecule is given by Fr is equal to summation Gr into e raised to the power minus epsilon r divided by kT, equation number 1. From quantum mechanical principles, the rotational energy epsilon r for a diatomic molecule at the jth quantum level is given by epsilon r, that is equal to j into j plus 1 h square divided by 8I pi square, equation 2. So this equation 2 is the equation for rotational energy epsilon r for a diatomic molecule for jth quantum level. And in this equation, I is the moment of inertia which can be calculated by mu into r square. As the axis of rotation is defined by two coordinates, which means that there are two rotational degrees of freedom. Each quantum level of rotation will bring in two possible modes of distribution of rotational energy. So the statistical weight factor J is given by 2J plus 1. Hence, equation 1 becomes here Fr, that is equal to, here we are representing summation 2J plus 1, that is the statistical weight factor J is given by 2J plus 1. So 2j plus 1 into e raised to the power minus j into j plus 1 h square divided by 8 pi square I kt, that is equation number 3. Now since the energy levels are closely spaced, the summation can be replaced by integration. So this summation we are going to replace by integration, and the equation becomes f dash r is equal to integral 0 to infinity 2j plus 1 e raised to the power minus j into j plus 1 into h square divided by 8 pi square I kt into dj, that is equal to 0 to infinity 2j plus 1 e raised to the power minus j into j plus 1 into beta into dj, that is equation 4. Now what is this beta here? Beta is h square divided by 8 pi square I kt. Here we have written h square divided by 8 pi square I kt. For this we have represented it by another constant, that is beta. Now suppose now you want to evaluate this integral. So for that we have to make certain assumption. Suppose if you introduce a mathematical function g, that is equal to j into j plus 1, and if you differentiate this, g is equal to j into j plus 1, on differentiating it we get dg is equal to 2j plus 1 into dj. So hence representing 2j plus 1 into dj by dg. Okay, so in this particular equation or this equation, 2j plus 1 into dj, that is replaced by another function, that is dg. So hence equation 2 becomes fr is equal to integral 0 to infinity e raised to the power minus g into beta. So here we have assumed that j into j plus 1, that is g, and if you represent this, 2j plus 1 into dj comes out to be dg. So here in this equation, for 2j plus 1 into dj we have written dg, and j into j plus 1 we have written g. So the equation reduces to a smaller form. Fr is equal to summation 0 to infinity e raised to the power minus g into beta into dg, and the value of this according to the standard integral formula comes out to be 1 upon beta. Now beta is h square divided by 8 pi square I kt. So here we have written the value of beta, and the equation becomes 8 pi square I kt divided by h square, that is equation 5. Since here we are representing beta by this, okay, so that this will go in the numerator. This is equation 5. The value of rotational partition function Fr, it is valid for heteronuclear molecules like NO, HCl. Here you have different atoms, etc. Whereas in the case of homonuclear molecules like O2, N2, etc., where the molecule when reversed becomes indistinguishable from the initial state, then the partition function is to be divided by the number of symmetry with 2. That means in case of homonuclear molecules where both the two atoms are the same, then the partition function has to be divided by symmetry, that is 2. So for homonuclear molecules, the formula for partition function, that is rotational partition function, becomes Fr is equal to 8 pi square I kt divided by 2h square. This 2 you are writing because the molecule is homonuclear molecule. In general, when the symmetry number is to be represented by delta, then partition function is Fr is equal to 8 I kt pi square divided by sigma h square. So instead of 2, we are writing the formula for in case of general condition. Equation 6 holds good for diatomic molecules other than hydrogen and deuterium. So the rotational partition function can also be represented by another formula, that is Fr is equal to T divided by sigma theta rotational. Even this is one of the formula for representing rotational partition function. In this particular formula for homonuclear diatomic molecules like H2N2O2, the value of sigma is 2, and for heteronuclear diatomic molecules like carbon monoxide, nitric oxide, HCl, etc., the value of sigma is 2. Fr is equal to Kt divided by sigma hCb, where B is the rotational constant. This is also another formula for writing the rotational partition function. Now for polyatomic molecules, the evaluation of the partition function are quite similar to those described for diatomic molecules. It is, however, supposed that ground state of the polyatomic molecule consists of a single electronic level, and that excited state make no contribution to the total partition function. So assuming the molecule to behave like a rigid rotator, the rotational partition function excluding the nuclear spin factor for a non-linear molecule is given by Fr is equal to 8 pi square into 8 pi cube ABC raised to the power half into Kt raised to the power 3 upon 2 divided by sigma h square. Now by this ABC, these are the moments of inertia of the molecule with respect to the three perpendicular axes, that is x, y and z. Now we will discuss the third type of partition function, that is the vibrational partition function. The partition function for vibrational energy of a diatomic molecule is given by Fv is equal to summation Gv e raised to the power minus epsilon v by kT. Suppose this is equation 1. As the statistical weight of each vibrational level is unity, we can write for Gv, we will write unity. So Fv is equal to summation e raised to the power minus epsilon v by kT, equation 2. That is, as the statistical weight of each vibration level is unity, we have to write Gv is equal to 1. For a diatomic molecule vibrating as a simple harmonic oscillator, the vibrational energy levels are obtained by the solution of the Schrodinger's wave equation. And at the nth quantum level, the vibrational energy of a diatomic molecule is given by epsilon v, that is equal to n plus half into h nu, where nu is the fundamental frequency of vibration and n is an integer which is having values 0, 1, 2, 3, etc. Therefore, from equation 2, Fv is equal to summation e raised to the power, we are substituting epsilon v by n plus half h nu. So the equation 2 becomes Fv is equal to summation 0 to infinity e raised to the power minus n plus half into h nu divided by kT. Now this is again a series formula, and the expansion of series we are writing here e raised to the power minus half h nu by kT in bracket 1 plus e raised to the power minus h nu by kT plus e raised to the power minus 2 h nu by kT plus and so on plus e raised to the power minus I, this is a general term, minus I into h nu divided by kT plus and so on. So this is a standard mathematical series whose expansion is given here. Now this we can write as e raised to the power minus half h nu by kT, and for this bracket we can write 1 minus e raised to the power minus h nu by kT raised to the power minus 1. As this series 1 minus e raised to the power minus x raised to the power minus 1, the expansion of this series is given by 1 plus e raised to the power minus x plus e raised to the power minus 2x plus e raised to the power minus 3x plus and so on plus e raised to the power minus ix plus and so on. Now the quantity h nu by kT is very small, and as a first approximation, therefore Fv is equal to 1 minus e raised to the power minus h nu by kT raised to the power minus 1, and this we can write as 1 divided by, if you write this in the denominator, it will become positive 1 divided by 1 minus e raised to the power minus h nu by kT, and that we can also express as 1 divided by 1 minus e raised to the power minus theta vibrational divided by t. The value of nu, that is the vibrational frequency, is equal to c into w, where c is the velocity of the light and w centimeter inverse is the vibrational frequency in wave numbers of the given oscillator. Hence, the vibrational partition function Fv is equal to 1 minus e raised to the power minus h c into w divided by kT. Here we are representing this nu as equal to c into w. So the equation becomes this particular equation, which we can express in the form of equation 5 if you take this in the denominator. So equation 5 may be used for vibrational partition function of a diatomic molecule at all temperature. The only approximation involved is that the oscillations are supposed to be harmonic in nature. Now we will come to the last partition function, that is the electronic partition function. Though it is possible in principle to solve the Schrodinger's equation for the electronic states and energies of molecules, it is more convenient to obtain this information from the spectroscopic data. For most of the molecules, the excited electronic energy levels lie so far above the ground state compared with kT, that is a typical excited state value being greater than 2 electron volt, that is nearly equal to 3 multiplied by 10 to the power of minus 19 joules, that all the molecules may be considered to be in the ground state at ordinary temperature. So thus contribution to the electronic partition function arising from excited electronic states may be neglected. And the electronic partition function is given by the formula Q electronic, that is equal to summation G electronic into I into e raised to the power minus epsilon I by kT, that is equal to G0 into E0 plus G1 into e raised to the power minus epsilon 1 by kT plus Ge e raised to the power minus epsilon 2 by kT plus and so on. So neglecting this higher excitation energy level, the value you can write as G0. Since the second, third and subsequent terms are considered to be negligible, these second, third and subsequent terms are considered to be negligible. Thus, the electronic partition function is simply the degeneracy G0 of the ground electronic state. In the Russell-Saunders coupling scheme, the degeneracy of an atomic electronic level is given by G0 is equal to 2J plus 1, where J is the total angular momentum quantum number. The degeneracies of the electronic ground states of atoms are given in the table below. This table represents the ground state electronic degeneracies of atom H, that is hydrogen, helium, sodium, calcium, chlorine and lead, that is Pb. Here you can see the term symbol 2s plus 1 into Lj, and this is 2s half, 1s0, 2s half, 1s0, 2p, 3 upon 2, 3p0. And G0, that is the degeneracy, is given by 2j plus 1. The value comes out for hydrogen 2, for helium 1, for Na the value comes out to be 2, for calcium 1, for chlorine 4 and for lead 1. The term symbol 2s plus 1 into Lj. It is a shorthand notation for all the angular momenta of an atom, that is the spin angular momentum S, the orbital angular momentum L and the total angular momentum J. Okay. So what does this term symbol 2s plus 1 into Lj represent? It is a shorthand notation to represent all angular momenta of an atom, that is spin angular momentum S, orbital angular momentum L and the total angular momentum J. So mathematically S is equal to summation Si, L is equal to summation Li and J is equal to L plus S for atoms with atomic numbers, that is Z is less than or equal to 30, where Si and Li are respectively the spins and the orbital angular momenta of the individual electrons in the atom. The ground electronic states of free atoms are generally degenerate. For hydrogen atom with electronic configuration 1s1, the spin S is equal to half and the value of L is equal to 0, so that J is equal to L plus S, that is half. And G0, the value comes out to be 2 into half plus 1, that is 2. For helium atom with electronic configuration 1s2, the value of S is half minus half, that is 0, and L is equal to 0, so that J is equal to 0 and hence the value of G0 is equal to 1. Thus for hydrogen atom, the Q electronic, that is the partition function, is 2, and for helium atom, the value of electronic partition function is 1. Similarly, the ground state of chlorine atom has a degeneracy of 4, so that the value of the electronic partition function comes out to be 4. The ground electronic states of most molecules and stable ions are invariably non-degenerate, that is, they are singlet. So in that case, the value of G0 is equal to 1 and hence electronic partition function is equal to 1. So this was all about the different types of partition function, that is, we have discussed the vibrational partition function, the rotational partition function, the electronic partition function, and I hope you have understood all the 4 types of partition function. And do like, share and subscribe. The topic is very important. Thank you.